Welcome back everyone. Let us continue our discussion and study the relation of mass flow rate and the energy involved. According to classical thermodynamics, the energy added through heat transfer to a closed system and energy leaving the closed system to be net heat work done by the system. This is normally represented by the sum of three separate energy, which includes internal, kinetic, and potential energy. However, since there is no elevation change nor direction change in a closed system, the potential and kinetic energy are normally assumed as zero. However, in an open system or a system with control volume having mass crossing the system boundary, the mass carries energy with it. Thus, the energy content of the control volume may change caused by mass change in the control volume. Thus, here it is said the energy of flow is the work or energy required to push the mass into or out of the control volume. This work is necessary for maintaining a continuous flow through a control volume. Let us look into the original definition of force. F equals to PA, and for work of a flow, W equals to FL, and equating F equals to PA, thus we can relate that the work of a flow is equals to PV, pressure and volume. With this new information, let us review our energy balance. For a non-flowing fluid, we have internal energy, kinetic energy, and potential energy, which is basically equals to U plus V squared over 2 plus GZ. Now, we're going to take account for a flowing fluid. We introduce the term PV, which we have discussed before, into the energy balance equations, like so. Now, instead of E, now we have theta. Theta equals to PV plus E. This equation is for a moving fluid. Equating the previous equations here into our moving fluid energy equations, we have PV plus U plus KE and plus PE. Introducing enthalpy H. Enthalpy H equals to internal energy plus moving fluid work. Enthalpy H is actually a combination of internal energy and the moving fluid energy. Thus, again for clarity, for a moving fluid, the energy balance is presented with the presence of enthalpy. This term here means for enthalpy plus the kinetic energy and for the potential energy. For non-moving fluid, we have internal energy only without the terms PV. With the term PV introduced into our energy balance, and by introducing the terms enthalpy, now we can calculate the rate of energy transported for a moving fluid, as shown here and as shown in these energy equations. Again, in our thermodynamic analysis, we tend to simplify our thermodynamic process, thus assuming the kinetic and potential energies. Like here, these kinetic and potential energies are negligible. We have the net energy rate of a change as m dot h, or in terms of rate. However, for a compressible flow, the energy equation is solved using integration method as shown in these equations, which is a lengthy process overall. Thank you for your time. Hope to see you on our next video on engineering thermodynamics.